So this is the second part of the quantum wells and heat diffusion project. This is actually the heat diffusion part. So first what we want to do is be clear and close all so that the program works later. And for task 2, we're asked to define the relationship between alpha and k. So first we define alpha, that's alpha up there, A. And second, we set these variables to be symbolic so that they are not represented as undefined variables when we work later on in deriving it. So this is the equation that we use. First, we find the derivative in respect to time, and we find the derivative in respect to x, y, and z twice. And we can add that up to become, we can define it as 1. So we add it all up. And using the equation that was given to find k, we have to set it equal to 0. And that means we have to put it all on one side. And so what we do is we take the derivative in respect to time and we divide the sum of all the second derivatives. After that, we subtract alpha, and then we can solve the equation to find k using the solve function. And when we did that, we found that k is equal to alpha, which is 25,000. For task T, we are supposed to ask the user to input the point where the x, y, and z coordinate where the heat source starts. So to ask, I set a while loop to make it so that if the inputted x or y or z coordinate is out of range, it will be denied and the while loop will continue. If they didn't enter anything, we will set the point to 0. And if it's within the range, it will work and the while loop will let the program continue. So it does this for x, it does it for y, and for z. So in task 4, after you've defined your x naught, y naught, and z naught, you have to ask the user to define the time, the end time. It's basically where you're finding your solution, but it's also the end time for later on when we're plotting it. So you ask them to define t, and if t is negative or equals to 0, the while loop will reject it and it will start over again because time has to be a positive integer. So in task 4, we first define the solution array heat D, and it's a 4-dimensional array for x, for the for the index x, y, z, and time t. So it's 4 dimensions, 41, 41, 41, and t. That's how big the t array is. And so we define x, y, and z, and t. So x, y, and z is from -400 to 400 in 20-point intervals, and t is just 1 to the end time that the user picked. Since indexes can't be negative, we use k, h, and I, and j to define the indexes for x, y, z, and t, respectively, and that will be in the for loop. So for k equals 1 to length of t, which is the length of time, these are the indexes to call out the variables in x, y, z, t. So in the equation, we're actually using these numbers, -400 to 400 in 20-point intervals, but to put it back into the 4-dimensional array, we use the indexes that we just created, k, h, I, and j. because indexes cannot be negative. So now we put the equation and we have our solution, and it fills up the heat D array, which is the 4-dimensional array. And we are asked to provide the solutions at z on z equals 0 plane at time t. So the solutions on the z equals 0 plane at time t. And this is 21 because the 21st, the index, 21st variable value of the array z is actually 0. And we display the solution. So for task
So task 5, it asked us to plot the solution. So to do this, first we created a figure handle called figure 1, and we use the surf function to graph the surface. And then in the surf function we have x and y inputs to make the surface, and then heat D would be the input that affects the height of the surface. And then we have the label here, title, for the heat diffusion at time t, and then the x, y, and z label to label each of the individual axes. And then once we set up the plot, we had to make a contour plot. So that was the task 6. So we created another figure 2, and then for this one, instead of using the surf function, we used the contour function with x and y, setting the range of the plot, and then this is what actually makes the plot, the heat D input. And then we set this whole function to variable c so that we can label it later. And then we use the c label function to give the contour graph numbers for the changes in height. And then title function to give the contour plotted title and x and y labels for labels. And for task 7, this task asked us to make a movie showing the diffusion of heat. So to do this, we use a for loop to go through each individual time, depending on what time the user set, so that it would show the evolution of heat for each second progressively. So it's just like during task 5, except it's inside for loop. So it's from 1 to t being the user input, and then surf function with x, y, and the heat D input to create the surface, and then title, x label, y label, and z label to label the graph, and then pause with 0.5. This is what stops the movie, kind of. This is what stops each individual scene for half a second, so that it actually looks like a movie. And then once it reaches here, it just repeats. And then this is another movie, but this one is to scale. And this one shows like a faraway scene so that you can actually see everything going on. This movie shows like a closer up scene so you can see the diffusion of heat more closely, so you can see it spreading. But it's the same color except for this. This is the scale to make it farther away. Everything's the same for the bonus except for x, y, and z. X not, y not, and z.
So for the bonus, everything's the same except for x naught, y naught, and z naught. We just set it to the point where it was asked, which is 0, 0, and 400. which is exactly the same as well. So if we run the program, let's say enter, enter, enter. Since we didn't give a value, it would be set to 0. Let's say 10. This is the given solution. This is the heat diffusion at time t. This is the movie showing the scale, to scale. So you can see. And this is the bonus at time t. This is the